Okay, so the purpose of this video is going to be as a reference where we try and summarize some of what we've learned about the electric field and the electric potential, kind of compare and contrast them because they can look kind of similar and that can be a source of confusion, and so we wanted to put all of this in one place. So let's get to it. So I'm going to try and organize this as a chart where we talk about the electric field and the electric potential, how they're the same, how they're different, that kind of thing. So let's put in this first column the electric field, and here we're going to have the electric potential, or potential as we usually just call it. I don't know why I did that. Let's see. So, all right. Electric field. Well, first of all, what are these things? Let's put a definition. So the electric field, as we talked about, is the force per charge. Force per charge. F per Q is E. While the electric potential is energy per charge, so potential energy per Q. So U per Q equals V. Okay. And right along those lines, what are the units for these things? Well, let's see. So force per charge, newtons per coulomb. Energy per charge would be joules per coulomb. And this gets its own name. This is the volt. Okay. What else? So what about the type of number? So electric field, this is a vector quantity. It has direction. And the electric potential is a scalar. It has no direction. All right, what about superposition? Can you do superposition? And the answer for both of these is yes. When you're talking about the electric field, this is a vector addition problem. When you're talking about the electric potential, it is a scalar operation. In other words, when you're adding vectors to do electric field addition, you have to pay attention to the directions, make sure the directions are taken care of. Whereas with the scalar, with the potential, you just need to know how far away they are. You don't actually care about the direction because it's not a vector quantity. Okay. What else? Let me put this here. Let's say you want to calculate one from the other. So what I mean is, how do we connect one to the other? And there's a calculus connection in both cases. So to get the electric field from the electric potential, we know that E is equal to the negative gradient of V. That's weird. It made like auto drew my. So this is, oh, weird. Okay. Wants to make my triangle perfect for some reason. This is equal to the negative gradient of the potential. And when we're talking about, so in general, this could be this could depend on derivatives in x, y, and z, or it could depend on derivatives in r, theta, and phi, or other coordinate systems. For our purposes, since we're working with basically exclusively spherically and cylindrically symmetrical situations, so let me put for spherically and cylindrically symmetrical situations, we can basically think of this as E is essentially the negative derivative with respect to r of v of r. And then that gradient has to impart direction. And so if we're talking about things that are symmetrical in r, there would be a factor of r hat, the unit vector, to indicate that the electric field points in the r hat direction. So that's our mathematical operation to get E from V. The counterpart to this would be, how do you get V from E? And that is integration. So this looks like this. Now, in general, this would involve a dot product. It depends on both the direction of the electric field and the direction that you're integrating in. And as you know, you can think of that as a factor of cosine theta. So basically, when we're considering situations that are only spherically symmetrical, so you think like the point charge or something like that, the only direction that's going to matter, so in general this is dl, the only direction though that's going to matter is in r, because you're going either towards or away from what you're talking about. And so likewise, for spherically and cylindrically symmetrical situations, let me just put again here. So for spherical and cylindrical symmetry, this is going to become just an integral over r. Okay. Oh, and maybe just to make this a little more clear, the idea being that E is a function of r, and so that all that matters is integration in r. In other words, if you don't change the distance away, so imagine you integrate like this, and then you go sort of side to side, that will have no bearing on the potential. It only depends on how far away you are. So these are the two mathematical points, or how you kind of convert E to V and V to E using calculus. And then what are our common configurations? So we have the point charge. So think of that as, you know, our charge Q. What does the electric field look like for this? Well, this is the familiar, hopefully, KQ over R squared, which we kind of originally talked about from the perspective of Coulomb's law, and later we derived using Gauss's law. That's the electric field. What's the potential for this? Well, it looks very similar, KQ over R. Now notice it has no direction, no factor of R hat, and it depends on 1 over R instead of 1 over R squared. And we could compare diagrams for this too, like the electric field would have arrows that point. There are electric field lines. We could also draw a diagram for this in terms of potential, and we did this in class, equipotentials. And for a spherical symmetry like this, they would be circles. Equipotentials. So that's the point charge configuration. Oh, and we can add here, you know, you can show getting one from the other. So right, where does this V come from? Well, if you integrate, right, this would be the integral of E, and E was KQ over R squared. So what does this become? This becomes an integral negative. Let's pull out KQ. This R hat dot dr, that will just become an integral of 1 over R squared. What is the integral of 1 over R squared? You get negative 1 over R. negative kq times negative 1 over r. And in general, this would be this is an indefinite integral, so we would have a factor of c. But by convention, we set the constant to be 0 so that the potential goes away when r is large. And so notice this gives us our kq over r. Okay? And then if we wanted to go back, you want E, we can kind of close the loop here. E so applying our definition, the derivative of kq over r, negative, times a factor of r hat. Well, that's r to the minus 1, so the derivative of that would be negative r to the minus 2. Let me just put it in 2 steps to make this very explicit. So what does that give us? Our negative signs cancel out. We get back our kq over r squared in the r hat direction. So this is just, kind of the simplest scenario to show us this connection between E and V using the calculus. All right, so that's for the point charge. So what other configurations do we have? Well, probably the next most important would be the line of charge. So the point charge, then the line of charge, or the charged wire scenario. So that was basically like a line, and we imagine it extends in both directions. It's basically infinite in length, and it's charged up, and it has some length, linear charge density lambda, q per unit length. And so what does the electric field look like for this configuration? We got this from integrating Coulomb's law, and we also can get this from Gauss's law, and that looked like lambda over 2 pi epsilon naught r. And this was, it pointed basically radially away from the wire. There's no component to the electric field that points along the wire. And so that's the electric field. What did the potential look like for this? Well, how would we get this? We saw it in lab. We know that it's going to go like integrating E. And so we can talk about this in a couple different ways. If we look at the indefinite integral case, so this would be, put all of our stuff in here, integrate this with respect to r. We could pull out all the constants and everything, charge density, these other constants. You have an integral of 1 over r. And what does that look like? Well, that'll give you log r. And so the indefinite integral case would look something like this. Plus some constant. And you'll notice this is negative. But remember the constant. So really what matters is the change in potential. But this would be sort of the general solution that you'd get for the indefinite integral. And the main thing is that it depends on log of r, and the natural log of r. And we saw this in lab. So this is the kind of indefinite integral case. And here, let me it's a little bit of a tangent, but let's also look at the definite integral case. So because this is it's oftentimes that you see this kind of situation. You want to know from one radius to some other radius. And so you care about the limits. And so what would it look like in that case? Well, this integral would now go from, say, r naught to r. And, the contents inside of here are the same. Same approach. You get the same, the same thing, log of r, except now you're evaluating this from r naught to r. And so what does that look like? Well, lambda, all of our constants, you would have factor of ln of r minus ln of r naught. And so if you remember your rules for logs, you can write that as a ratio. And often what is done with this case is to write this. So instead of ln of r over r naught, you flip this around to get rid of the negative sign. So you can write this concisely as ln of r naught over r. So this would be the definite integral case. Definite integral case. And you're going, from r naught to r. So it's the same function and everything. It's just that this now incorporates limits, and there's a lot of circumstances where that's maybe a little more useful. So that's the line of charge. So there's one last symmetry, one last geometry that we want to look at. We've looked at spherically symmetrical. We looked at cylindrically symmetrical. So kind of our last case would be the constant or plane symmetry. So we encountered this. This was the the plane of charge. Really, we're going to focus on the two planes, like the parallel plate configuration. But this is the plane of charge. Let me label it this way: plane of charge, two plates or parallel plates slash constant E. This is the main, the main pertinent thing. And this relied on, well, let's look at them both. The single plane, basically, we imagine it's very large. And the electric field, of course, is perpendicular to the surface. And, this is all charged up or whatever. And in fact, it would have some, surface charge density sigma that would be, correspond to the Q per area on the surface. And we derived with Gauss's law that the electric field for this configuration would be sigma over 2 epsilon naught. And remember, the electric field points both directions. And so kind of related to this is, well, then if you have two plates, so now just looking at it on edge, and if one of these is positive and one of these is negative, you would have field lines that would be pointing away from the positive plate towards the negative plate. And what would happen is that the fields outside of the plates would cancel, but the fields inside would add. And so E for this configuration would be 2 times the above, and so you'd have just sigma over epsilon naught. So this is the single plane. This is the parallel planes, parallel plate configuration. And so that's the electric field. And we haven't been. This isn't in in R per se, so I don't have a factor of R hat there, but you could imagine this, if you specified your coordinate system such that this was like Z or something, then this would have a factor of, K hat in it, something like that. It's going to depend on how the problem is defined. But what's the potential? Well, the potential in this case, starting from the same point, integrating E. Now, integrating E in this case is going to be really simple because E is basically, it's a constant. So, but let's think of it as, our L direction would be going this way, but our E direction would be going this way. So notice that those are pointed in opposite directions. And so this E dot dl, that cosine, because remember, you can think of this as E dl cosine theta. If those are 180 degrees, theta is 180 degrees, then you would pick up a factor of -1 from that. And then also notice that if E is constant, as it is in this case, you could pull E out of the integration. So you would have E times this factor of -1 from the dot product. And then the integral of dl is just the distance between the plates. So kind of confusingly, we usually call this d. If the plates are separated by a distance d, then what would this become? Well, V would just be E times D. And so this is our expression for the potential between the parallel plate configuration. It's just the electric field, that constant field, times the distance between the plates. And then vice versa, you could express E in terms of V as V over D. And there are circumstances where that's a nice it's a nice way to talk about it. So this is in terms of voltage, whereas this is in terms of surface charge density and epsilon naught. So sometimes you want to talk about it's easier to work with the voltage and the geometry, the distance between the plates. Other times you might be interested in the surface charge density and epsilon naught. It's going to depend, but that gives us, that's kind of our last geometry that we wanted to mention. So hopefully this gives you a little bit more clarity to have a reference that has kind of the potential and the electric field for the different geometries that we've talked about.